In this slideshow, I will give you a very gentle, mostly non-technical introduction into our favorite verification technology, static program analysis. Let me first tell you who I am. Well, not really. That would take too long and would be not really interesting. But I will give you some facts about my professional life.
I'm always impressed when I look at this list, I must confess. The most important fact in this list is that I am one of the founders of Absinthe and that all other co-founders were my doctoral students. I start by explaining what I mean by verification. The word verification is heavily used in industry for any activity trying to strengthen one's belief in the correct functioning of a piece of software or hardware. So, superficially looking over a program code to discover the absence of apparent bugs, some may call verification. We want to be more precise. First, we are using verification in a strong sense. If some property of a program is verified, then this program is guaranteed to have this property. This is very important. The technique I present is able to deliver such guarantees. Then we make a difference between different types of correctness properties. Functional correctness means that the program does what its specification says. The specification, however, may be wrong. That is, it does not describe what the client or the user had in mind, but this has to be checked separately by an activity often called validation. Then we have non-functional correctness properties. For instance, the absence of runtime errors, like division by zero, index out of bounds, arithmetic over or underflows, large floating point rounding errors. Then the satisfaction of space constraints, namely that the program does not exceed the space allocated to it. And finally, the satisfaction of timing constraints, that the program does not execute longer than its deadline permits. There's a whole zoo of verification techniques that people call actually verification techniques, but not all of them possessing the ability to give guarantees, as we will see. Message 1 is very bad news. There is no silver bullet. No solution to the verification problem exists that has all properties one would like it to have. What are these properties that we would like it to have? It should be automatic, that is push button, and not need a little help by our friend the user. It should be powerful, that is able to prove non-trivial properties. It should be sound, never prove the property if it does not hold, and it should be complete, that is always prove the property if it holds. Let us consider the last two properties more closely because they are extremely important. If a verification method or tool for a certain type of correctness property is sound, it will never claim that the program has this property when in fact the program does not have the property. So it will never falsely claim correctness. If a method or tool is complete for a certain type of correctness property, it will prove correctness for any program that has this property. It will never fail to declare a correct program as being correct. So it will never say that the program is incorrect, and it will never warn the program may be incorrect. This bad news comes from Rice's theorem. Formally, Rice's theorem says that all non-trivial properties of program behavior in a Turing-complete programming language are undecidable. Well, there is a lot of unknown terminology in this statement. Turing-complete programming languages are those that, intuitively spoken, can express anything you want to express. For this talk, it suffices to say that the programming language developers are using, like C or Java, are Turing-complete. Undecidability of a property means there is no automatic method that is sound and complete. In brief, Rice's theorem tells us that our wish list for a verification method given above is too long. We can't have all of it, automatic, powerful, sound, and complete at the same time. The question is, what should we erase from our wish list? If we are ready to give up the requirements to be automatic, and thus expect a little, in fact quite a bit of help from our friend, the user, the developer, or the verifier, we may use some way of deductive verification supported by interactive theorem provers or similar techniques. We prefer to keep soundness and automatic way of working, but to give up completeness. You will see the consequences and nature of the above methods on the following slides. Method 2 is more educational. Don't give up searching for a method that works. Even if you were disappointed by an implementation of method X by tool Y, try another tool implementing method X if method X is promising. Method 3 tries to describe what a customer of a usable and effective verification method could expect. Our tools should decrease at customers the number of recalls by X%, the risk of punitive damages by Y%, the threat to end up in prison due to a failure of a safety-critical embedded system he developed and marketed. Here's a list of software errors that made the news. They seem to be a bit outdated, but don't worry. Maybe I should say do worry. The same errors appear in current software. For each incident, the type of software error is given in brackets. The first example is the time drift in Patriot rockets in 1991, caused by a rounding error. Developers often think they are using real numbers, like you know them from high school. In fact, they are using floating point numbers, and their values deviate from the values of the real numbers the developer has in mind. Over the time of a long calculation, the differences between a calculation using real numbers and the same calculation using floating point numbers may become significant, and this difference led the Patriot rockets to miss their targets. The next example is the crash of a railway switch controller in 1995 in Hamburg-Altona, caused by a stack overflow. This is an example of a software exceeding its space constraints and overwriting something relevant, either code or data. Then the explosion of the Ariane 5 rocket, 1996, caused by an arithmetic overflow. Arithmetic overflows may cause quite unexpected results of calculations and correspondingly wrong reactions of computer-controlled systems, in the case given the crash of the Ariane 5 rocket. Then the Toyota unintended acceleration incidents, most likely caused by a stack overflow. This is a long story that cost several people their lives and Toyota a lot of money. There were many explanations given by Toyota why their Camry cars would unintendedly accelerate, starting with the infamous floor mat coiling up under the brake pedal. However, the best explanation of the incidents is that a stack overflow happened, erasing important routines allocated in memory just above the runtime stack. Then the AECL Ferrac 25 incident caused by race condition and arithmetic overflow. This was a rather tragic incident with a radiation engine. This radiation engine counted errors in the counter starting at 0, and when the counter overflowed, it went down to 0. However, 0 indicated no error, so the radiation engine would continue after checking the counter and finding that the counter was at 0. And so it killed several people by exposing them to more radiation that they could survive. So what is a race condition? A set of concurrently executing programs exhibits a race condition if these programs share a variable and the value of the variable depends on the relative speed of the programs sharing the variable. In the example, if program A writes first, variable x will receive value 0. And if A will read before B writes, it will read 0. However, if between A's write and read, B will have written 1 into X, A will read a 1. After this long introduction, we come to different approaches to functional verification. That is, the verification of functional correctness. Remember, functional correctness means that a program does what its specification says. We have a program and a correctness statement describing all behaviors of the program. We depict the set of all behaviors of the program by the contents of the circle. I repeat my warning. Don't expect a verification method that is powerful, automatic, sound, and complete. As already said above, we may decide to give up the automatic way of working and involve the user and keep soundness and completeness. This makes sense and has been done in academic environments by highly skilled people. A good example is ComCert, the first verified optimizing C compiler. This was a highly praised research project with a practically usable result. It is the only C compiler you can trust. See John Regier's study of errors in C compilers. We now introduce our running example for the analysis of a non-functional property. We are trying to show the absence of division by 0. Let us consider the occurrence of a fraction in a program. The easy cases are that the denominator is a constant. We have found a definite runtime error if this constant is 0. It occurs in reachable code, and they are right. However, the interesting insight on this slide is that the question is non-trivial if the fraction is x divided by y, that is, a variable divided by a variable, or divided by an expression containing a variable. Why is this interesting? Well, we want to answer the question whether the evaluation of this expression can never cause a division by 0. To answer this question positively, that is, there is no runtime error caused by division by 0, we must know that y will never have the value 0. That is, in no execution of the program in which this expression occurs, whatever the input values to the program are, and consequently on whichever program path execution arrived at this expression, no division by 0 happens. One way to know this is to know all values for y that are possible when execution reaches this expression. We will later see that there are other ways. Let's now look at one method to attack our problem to make sure that the program does not contain certain errors. Testing is highly popular. Again, we have the set of all program behaviors, and we have some bugs in the program. These will manifest, as we assume, in different behaviors. We run some tests which will trigger the execution of a certain subset of all behaviors, named test cases in the slide. We consider exhaustive testing, which would trigger all behaviors, as unrealistic. Let us now clarify a terminology that is often used in a confusing way. All verification methods attempt to answer a correctness question. So the question we would ask is, does the program contain a certain type of error? A positive answer to this question would mean, yes, this program does contain this type of error. This true positive answer then signals the existence of a definite error. A negative answer means, no, this program does not contain this type of error. Now the interesting cases are negative answers. A false negative answer means the answer was no, this program does not contain this type of error. However, the answer was wrong, it may in fact contain this type of error. A false positive answer to the question above means the answer was yes, this program does contain this type of error. However, the answer was wrong, it does in fact not contain this type of error. Note that one may also ask the negated question. Does this program not contain this type of error, or is this program free of this type of error? All answers would correspondingly be turned around. Now back to testing. In general, the space of all program behaviors is too large to be exhaustively tested as stated above. So one tests a subset of all behaviors. All errors found in the subset are, assumed the tests are performed correctly, true errors. But what about the subset of program behaviors that are not tested? There may be program bugs lurking in this non-tested subset. These undetected errors are then false negatives. That is, we will claim that there is no error in the program, while in fact there is at least one that we did not discover. Coverage criteria are used to keep the unexplored subset of behaviors as small as possible, and thus the chances for false negatives as small as possible. Still, the old claim of Dijkstra holds: program testing can be used to show the presence of bugs, but never show their absence. Now let's apply testing to our running example. We want to find out whether x divided by y may cause a division by 0. We will detect the possible division by 0 if we test the program with an input value that leads to y having value 1 at this program point. On the other hand, we may test the program with many input values that don't lead to y having value 0, but there may exist another input value that would lead to y having value 0. In the latter cases, our tests would leave a false negative, an undetected error in the program. There is another warning about testing in place. Testing is typically done on the source level. At least one looks at the source level while one runs the compiled executable with test data. The test results are again interpreted looking at the source program. This implicitly assumes a correct compiler. However, if the compiler is not correct, which is the case for most compilers, the compiled executable program may perform something different from what the source tells you. The verified correctness properties on the source level are only guaranteed to hold for the executable level if one uses a verified compiler like CompCert, the first verified optimizing C compiler. The next so-called verification technique we will cover is bug chasing. These tools attempt to find many bugs in a short time, so they try to answer the question, are there errors in the program? How do they work? They typically look for patterns that signal errors. However, as I've tried to indicate in my graphics, some signaled errors would only occur in infeasible executions. That is, they do not correspond to legal behaviors of the program. So in the picture, the chased area is partly inside the set of all behaviors, partly outside. When we ask, are there bugs in the program? Bugs found in the intersection of both areas are true positives. Bugs found outside of the set of legal behaviors are false positives, also called false alarms. Bugs in legal behaviors not found by the bug chasing tool are false negatives. Remember that we discussed two properties of verification methods and tools in the context of decidability, namely soundness and completeness. Our conclusion about bug chasing tools is that they combine the worst of two worlds. They are neither sound nor complete. Back to our running example, the x divided by y. The tool may signal y equals 0, which may hold but might also not hold. The tool may signal x not equal to y, which may hold but might also not hold. So we really don't know much. Back to the foundations. Before we introduce our favorite method, let us repeat some fundamental insights we have gained in the introduction. We are interested in proving some correctness claim about a program. Rice's theorem says that all non-trivial program properties are undecidable. And undecidability of a property means there's no automatic method that always proves the property if it holds, this is completeness, never proves the property if it does not hold, that is soundness. The question is, how do we get out of this seemingly hopeless situation? So, sound static program analysis, also called abstract interpretation. We have seen earlier that we need to negate at least one of the properties we originally would have liked to have. Either involve the human, that is, give up the automatic way of working, or give up correctness and lose our ability to guarantee bug-freeness, give up completeness and risk to have false alarms. It is the latter option we choose. How do we do this? We consider a superset of behaviors, a set including all legal behaviors, but possibly also some infeasible behaviors. This is an over-approximation of the set of legal behaviors. If the analysis now determines that this superset does not contain errors, then the real set of behaviors does also not contain errors. On the other hand, the analysis may report some errors in the set of infeasible behaviors, that is, behaviors that cannot really happen. Since we are trying to prove some safety properties, namely that the program is free of a certain type of error, these errors the analysis reported are false negatives, also called false alarms. How does this apply to our running example? A sound analysis could compute enclosing intervals for the values of all program variables. So the analysis may compute the very small interval only containing 0 at the program point just before the occurrence of the fraction x divided by y. In this case, y is sure to have value 0 when execution reaches this program point. So we have discovered a definite runtime error. If the analysis computes an interval for y at this program point that does not contain 0, we are sure that by evaluating x divided by y, no division by 0 can happen. If, however, the interval includes 0, we are not sure what is the case. It could be that 0 is a potential value of y, so there is an execution in which y actually has the value 0, resulting in a division by 0. Or the 0 got into the interval by over-approximation. Then this would be a false alarm. Let me list some non-functional safety properties. Absence of runtime errors at program points, like division by 0, square root never of a negative number, arithmetic operation never causes underflow or overflow, array index is never out of bounds, dereference of a pointer never is a null pointer. Then there is the absence of race conditions. You may remember race conditions mentioned earlier on. Concurrent programs accessing shared variables have race conditions if they have potentially different outcomes depending on the order of writes to the shared variables. The absence of race conditions means the semantics of concurrent program does not depend on the relative speed of execution. Then the absence of timing accidents for instructions for a WCET analysis. These are safety properties one relies on to bound the execution time of instructions. When execution reaches the machine instructions at a program point, a safety property may be that memory access is always a cache hit, never misses a cache. That the pipeline unit is always available for dispatch of an operation, and that the bus access is never blocked. From such local safety properties at program points, we may be able to derive a global execution time bound. If this bound is small enough, we may be able to prove that the program terminates within a given deadline. Another relevant global program property is that the stacks never overflow. The cost. Static program analysis is a powerful verification technology. It needs educated users. Less so than other verification technologies like deductive verification, model checking. It distributes required competences better between the different types of people, like developers and users. It profits from information given by the user or the environment, like model information, constraints for the input and such. What are required or helpful competences of users? They should understand what errors the analysis is attempting to find. They should understand the program to analyze. And for absence worst case execution time analysis, they need to know their hardware platform. Otherwise, it is difficult to determine the timing behavior. The more the tool user understands about the program to analyze, the better information he can provide for the tool. The more precise will be the results in general. So how is the work distribution in static analysis? We should consider two times. Tool time, or better tool development time. At this time, the tool developer implements a static program analysis, which is dedicated to a certain set of correctness properties. This needs highly skilled people like the people at Absent. Then there's verification time. At this time, the system developer or the verification engineer applies the tool to the program. As said above, he may have to provide some information about the program and or the platform on which the program is to be executed. Static analyzers are dedicated to a certain set of correctness properties that can be tailored to these properties, which is good for scalability and usability. On this slide, you see the methods that are admitted to verification of automotive software. You see that static analysis based on abstract interpretation is recommended for all criticality levels, and that only these are sound and therefore able to give you guarantees. In this table, I tried to compare different methods. As for the properties being sound, being precise, being automatic, and able to scale. You see that static program analysis fares quite well. It is sound, but not complete. It is automatic, it is scalable, and one can trade efficiency for precision. As a conclusion, sound static analysis is a viable automatic verification method. It has a strong theoretical foundation in abstract interpretation, which makes tool qualification easier without foul compromises like proven in use. It provides a trade-off between efficiency and precision. It allows to tailor tools to applications, like you can adapt Absinthe runtime error analyzer ASTRE to different types of software or to software to be run in an AutoSAR context. It has a good distribution of required competences between the tool developer and the tool user.